Okay, hi everybody. Welcome to lecture 8 of 6 SO83 18-190. So tomorrow is the due date for problem set 4. So I hope you're enjoying it. Can we get a show of hands of everybody who's enjoying problem set 4 in the chat? Yes, great. So hopefully you're seeing these beautiful visualizations of these walkers moving around and, kind of colliding with each other and occasionally infecting each other. And so they should change color when they infect, right? That's the goal of the problem set.
Yeah, a couple of people who've got them working said they really thought this was pretty cool. So if you haven't gotten there yet,
this is one of the highlights of the course, in my opinion. And then, so our idea is that problem set 5 is due out tomorrow. Hopefully we'll get it out tomorrow. And that'll be sort of a capstone or it's not a final project. It's not actually a project. It's just a problem set. But the idea is it's going to be a problem set. It's the last problem set. So it'll be a problem set for 2 weeks worth of the course. So it'll sort of be, not quite twice the work, but it should be a bit more in depth or longer or more detailed. But so probably this one should have been the last problem set. Anyway, so hopefully that should be fun as well. Okay, I mean, fun. It depends if you think it's fun that a lot of people get infected by this disease. But okay, so today we are going to carry on where we started last time, looking at continuous random variables. So this is a subject it's a bit tricky. It has its trickiness, but so the idea of today is to try and make it as natural as possible by thinking of these continuous. So what is a continuous random variable? It's just a random thing that has values that can be any number in some continuous set. So any real number, basically, in some range. So last time we looked at dynamics of discrete stochastic processes in a bit more detail. So we wrote down equations that describe how the probabilities evolve. So we sort of assumed some kind of background in probability, but I don't want to emphasize that. We're just doing it in a kind of pretty intuitive way. So, the probability, what does it mean that the probability of jumping from one state to another is something? It means that at the next time step, the probability, multiplies the previous probability of being in the other state at the previous time step. And then you add all the probabilities together to get the total probability of being in a state at the next time step. So that is, the simplest example of a Markov chain, and which just means a discrete time process, a random process, where you have random variables at each step, and the random variables have a different, discrete values that they can take, and all these probabilities evolve in discrete time, and it's a Markov chain if the probability of being in some state at the next time depends only where you were at one previous time step. And we saw that in some cases, in many cases, what this will, not all cases, but usually you'll get a stationary distribution where the probability of being in some state at n at some time will converge as time goes to infinity to some limiting value, which represents the sort of long-term behavior of the system, the long-term dynamics of the system. And this is a very important concept in many areas. And so in the case of an epidemic, you might wonder, is it necessarily the case that everybody in the population gets infected? That's a very important question, and that is one of the questions that in my home country of the UK, initially, United Kingdom, initially they were saying that they were just going to let the epidemic run riot and do whatever it wanted and infect whatever proportion of the population it wanted to. And then hopefully it would only infect a certain proportion of the population. And once it had infected that proportion, it would die out. But actually, which may be true, but the proportion that it would need to infect was just so big that obviously that's not a good idea. And so then they started finally introducing social distancing, measures, or as I said in the problem set, that's a very terrible name, should be called physical distancing, because socially we actually want to be close to each other and connect, but physically we want to be far away from each other. So they finally introduced that, and hopefully...
Dave, you got to upload the slides again.
Sorry, I keep forgetting to put the slides up, thanks. Okay, I think they should be up. Let me know if they're not. And where is my window? Okay. So today we are going to look at this process where we start from a discrete random variable, a random variable which takes only discrete values, which is going to be a geometric random variable in today's case. And we're going to look at what's called the continuous limit, where we try and work out so basically, what we've been doing up to now is saying, okay, we can only jump every day. At the end of each day, we're going to see how did the number of infectious people change, how did the number of this and that change at the end of each day. But we didn't look in any detail, inside the day, what was the process that was going on and how was it evolving during that day. And so that gives us a discrete time evolution where we basically, when we sort of look at the numbers stay the same during the whole day, and then they sort of suddenly jump at the end of the day, or at midnight, they suddenly jump. If you're monitoring a website with these numbers, it gets updated at one particular moment, and until that moment, that website has the same numbers as it did for the whole of the previous day. And so we have a discrete random variable which jumps. At that particular moment, it jumps instantaneously from one value to another. And that's obviously very unrealistic in any kind of physical, well, it is and it isn't, right? So the number of people, of course, in the population the number of people is a discrete random variable. It has a discrete value. There are this number of people, and unfortunately, suddenly somebody dies at one particular moment, or leaves the population in some way, and so it suddenly changes. That's true, but if you want to know, when does a particular person get infected, that is not a discrete random variable, right? It's not they get infected at midnight only on each day. They can get infected anytime. And so we need to find some way of modeling that in a sensible way that somehow, recovers the same, statistics, the same dynamics as the discrete model. So that's what we're going to do. So we're going to take this continuous limit. So there's a mathematical way of doing it and a computational way of doing it, and we'll try and mix and match the two. I mean, they're the same, really. And that will lead us into a more general discussion of continuous probability distributions. So continuous random variables, I should write continuous random variables, which have continuous probability distribution. So that means a random variable which can take any continuous value in a range, as I said. And the concept of probability density function. Okay, so we'll start off as usual with our favorite random variable, which is a geometric random variable x. So let's recall from problem set 2, which we have been grading, we are grading, and we're sorry that it's a bit behind, but that we should be returning the grades very shortly before tomorrow, which is drop day. So we'll go back to what we were doing in problem set 2. What is a geometric random variable? It is a random variable that it has discrete values, and so things are happening at integer time steps, as I said, and so basically at each day we have a probability to recover or a probability to decay. If you're thinking about x as the number of radioactive atoms that are decaying with some rate, then you can also, this is also a model for that system, right? All good mathematical models can actually describe many different processes, and they fit, you know, each different process exactly as well as each other. And that's one of the advantages actually of having a mathematical description of a process, is that you can actually describe several different real world phenomena with the same model. And so once you've understood that mathematical model, you can describe it, you can use it to describe many different things. So the probability to decay at each time step was P. And what we, you know, what we realized both last week and in the problem set is that the probability that you decay at time n, right, that the decay time, so I called it tau at some point, I'll just call it x today. So this was called tau at some point. The probability that this random variable takes the value n, in other words, that the probability that the decay time, I'll just call it that instead of, you know, recovery, takes longer to say, decay time, the probability that the decay time is n is, right, so that's just, you know, any mathematical notation, you just have to think, well, what, you just have to decode that mathematical notation into words. So the probability P is the probability, this bold, blackboard bold P is the probability that this random variable takes the value n, is this product P times 1 minus P to the power n minus 1, and that holds for any value of the integer n going from 1 up to 2 up to, etc. So in principle, you can have an arbitrarily large value n. Yeah? So it can be 1 million, it can be 100, you know, million, it can be 10 to the power 100. But of course, the probability that it's going to be those huge values is very, very tiny, basically 0. And on the computer, it will be, you know, impossible to actually even measure that probability or even write it down. It'll just end up as 0. So in principle, this n has an infinite number of possible values, right? So the range of possible values of n, this sort of decay time, the time it took me to decay, is unbounded. Okay, so we're going to introduce a name for this and a notation. So if we have a random variable x, we'll call this probability, we'll call the probability mass function. And we'll write it as little f sub capital X. So the subscript is the name of the random variable. So this is the same as this. So this means the probability mass function fx sort of the random variable x, right? Is little f sub x of n, which I'm just defining to be the probability of the event that x has the value n. The probability that x takes the value n. Okay, so in the case of the geometric random variable x, we have that its probability mass function is equal to this thing, right? That actually defines a geometric random variable, and it's called a geometric random variable because we have a geometric distribution of, well, sorry, because we, you know, end up summing a geometric series, right? A geometric sequence is what we have to end up calculating with when we, and geometric, again, just means, you know, you're multiplying by this constant factor each time, right? So that's just, you know, notation and a name. Probability mass function is just this function that tells me what the probability is of having the value n of my random variable. And what do we know about that? One of the things we know is that, of course, fx of n must be bigger than or equal to 0 for all n, for all the possible values of n. It's a probability, so it has to be a positive number or 0. And it has to satisfy that the sum of all the possible outcome, all the possible values, the sum of the probabilities of those values have to be equal to 1. So that's sort of, you know, basic notions of probability theory. Just means that it's certain that it will eventually decay in this case. So it might be that you have some other system where you might never decay, but then you'll just add a sort of another additional state, which is sort of infinity, if you like, or just another state in your possible value number of states. And then if you add the probability of that state that you'll never decay, then that will give you 1. But there always has to be a probability 1 in total. Okay. So what we're going to try and do is work towards continuous time. We started doing this last time. So in order to do that, we have to actually introduce the notion of actual time instead of just steps. Right? So what does it mean for us to use time instead of number of steps? So basically what we're going to end up trying to do is we don't only want jumps at integer times, which is what we've had so far, whole numbers. What we want is we can think of taking jumps at a different set of times. And of course, these times in principle don't have to be equally spaced, but we're going to take equally spaced times. So you're just going to say, for example, well, okay, suppose instead of every day, I'm going to have something happen every hour. I'm going to measure the decay. I have a better monitoring system, and I can measure the decay now every hour instead of every day. Then I'm just going to define times t sub n to be n times delta. So delta is going to be the time between the decays, between the measurements. Right, okay. So now what can I do? So for example, if delta is a half, then I'll just jump twice per day if I'm thinking of like integers as being number of days. In principle, I would need an actual physical unit of time here. So delta equals 12 hours or delta equals 24 hours. And I would actually have to, and in Julia, we should actually remember to cover this. You can actually do calculations which involve units, which contain the units, and it will keep track of the units and make sure everything is correct. Okay, so what we're going to look to do is reproduce the same dynamics, right? So we already have our day dynamics with probability p per day to decay, and I want to know, one of the ways of thinking about this is how can I reproduce that dynamics, but by having decays happen every hour. So if I take the same probability to decay every hour, well, everything is going to sort of happen faster, right? Because if I have probability a half to decay every hour, obviously I'm going to decay much faster than if I have probability a half to decay every day. So that's not going to work. So the probability p of decaying at each time step, right? So must depend on how big this delta is, the time between those steps. So we're going to call that p of delta. So it's going to be a function of delta. So this is going to be the probability to decay at each step if the steps happen delta apart, happen a time delta apart. Okay. Okay, so it turns out that if you want to compare these two different processes, we cannot do it just by looking at these instantaneous jumps, because the jumps are happening at different times. And so that's not going to work. So what can we do instead? So this is what I started to do last time. What we're going to do is look at the total probability that I have jumped before a given time. Right? So this thing is the probability that I have x is the time to decay, right? My geometric random variable, the time to decay, time until I decay, or recover. I still can't spell. I can't write it. So that decay. Okay. Time until I decay. And so what I'm looking for is the probability that the time until I decay was less than or equal to n. That is the way that I'm going to be able to compare these two different things. And we're going to take all of the things that happen up until a given time, right? The probability that I've decayed by time n. And so the point of doing that is that now I can actually talk about any continuous time t. So I can actually talk about the same thing with a time t in here instead of a time n, a real t. And I'm going to call this thing, this probability, I'm going to call the cumulative distribution function. It's going to be capital F with a subscript x to mean the cumulative distribution function of the random variable x. of the random variable x. And yeah, as I said, now the point of doing this is that now I can actually talk about this probability that I'm less than or equal to t, and that's what I was drawing last time, and we'll draw that in a minute again. Okay, so this is, so I never used to understand what the point is of doing this, of passing to this cumulative distribution function instead, but I think this is one of the main reasons why you want to do it, actually. Because it's sort of less intuitive for a human, you know, this probability, because you're summing, yeah. So how do we actually calculate this thing? So you actually already calculated it in problem set 2. So so it looks something like this, right? It's a sum. It's a sum over, you know, so let's say f of x at some integer time n is the sum of j equals 1 up to that n of fx of j. So it's just the sum that you did in problem set 2 of all of the values of the probability that I decay at time j, of course, up until j equals n. It's kind of reasonable. But now, the not so reasonable thing, not so obvious thing is, what happens if I have a continuous time t? And the answer is, if I have a continuous time t, well, I have some number of things decaying at integer steps, and then suddenly I'm in the middle of a step, and I'm measuring what happens sort of in the middle of a step, or you know, in some non-integer time t. Well, all that I'm interested in is the decays that have happened at those integer steps before time t, right? And so what I need to find is the largest integer less than t, or less than or equal to t if t is exactly an integer. And that is what we call the floor of t, which you also saw in problem set 2. Although some people, you know, I guess I didn't really explain what floor was. I was hoping you would, you know, look it up and look in the documentation and see what was going on. And but this is a slightly different use of floor than you, well, yeah, actually distinctly different use of floor than what you were doing. But yeah, I hope it's clear that this is what I want here. But I want the biggest integer before t, right? And so we use this notation. It's like half of a square bracket, the bottom half of the square bracket, and then t. Right? So there's no a square bracket would have this sort of thing up here, but that's not there. It's just the bottom half. And then there's similarly a function, so this is the floor. And this other function t, which is the ceiling, this is the smallest integer bigger than or equal to t. That's the ceiling function. So this notation was introduced by Donald Knuth, who is one of them who, you know, most influential and prolific computer scientists of the 20th century. Apparently, he actually introduced this notation. You know, when he was the one who wrote TeX, which is this mathematical typesetting language, and
but not LaTeX.
But not LaTeX.
On TeX though.
Just plain TeX. And so he, I believe, you know, because he had written this huge book, a very important book, The Art of Computer Programming. And in the first edition, he had a lot of trouble with the typesetting of all these weird symbols like this one. And so he decided he would have to write his own mathematical typesetting program in order to be able to just use whatever weird and wonderful symbols and you know, put this up here and above the sum, etc.
Is that up there with some computer science professors writing their own Zoom application because they want to give classes?
Right, exactly. Okay, so this is the floor function. So you know, I always, my eyes always start glazing over when I see formulae with these kind of things. But I mean, if you just take a moment to think what's going on, it's just literally, oh yeah, I need an integer here, right? So, but t is a real number, so the only thing I need is to either take you know, to take either the integer before it or the integer after it, and it's just a way of turning a continuous time into a discrete time. And you just have to be careful whether you need the floor or the ceiling in any. So, some people use ceiling in their homework in problem set 2. It's perfectly fine to do that. It's perfectly reasonable, except that I asked you to use floor. So you shouldn't use ceiling if I asked you to use the floor, right? But it's perfectly fine, but whatever. Okay, so yeah, there is this function floor of t in Julia, and it will calculate this for you. Okay. So now what can we do? So that's the process X, right? So X is a stochastic process. What is that? It's just dynamics that's happening where there's some randomness involved. That's what a stochastic process means. So yeah, and so X is sort of evolving in time, and then there's some probability that X, well, yeah, okay, that's not quite true. Last time we looked at a stochastic process. Now we're not really looking at, there's an underlying stochastic process, and now X is not the stochastic process, it's just the result of the stochastic process or something. Okay. It's just like the first time, it's the first passage process, it's the first time that you hit 0 if you started at 1 and you're decayed. Or I think we did it the other way around. You started at 0 and you reach 1. Okay, anyway. So now we're going to think about this different process where you do jumps at times tn, which are not integers, right? Which is n times delta. And delta is not an integer in general. So we're going to call the resulting process y sub delta. Right? So X is the original process where I have jumps at time integer times. And Y sub delta is the process where I jump at times which are proportional to delta, which are multiples of delta. So this is also a discrete random variable. So just a reminder that a discrete random variable means a discrete valued random variable. The values of the random variable are discrete, the values that it takes. So Y is still one of these decay processes. It still tells me how many steps did you take to decay, right? How many steps I took to decay. But the steps are happening at different times now, right? So there's actually going to be two different things: how many steps I took and like when I took them. So its probability mass function is the same as, has the same form, I mean, as the probability mass function of X. So this is the probability that Y delta takes value n. In other words, the probability that this process that's taking steps at times n delta has decayed at time n. And remember that we called P of delta the probability of decaying at each step, right? At each step, if I'm taking steps of size delta. And so I get the same formula, but with P of delta instead of P. So this is a probability that it has decayed after n steps of size delta. But I want to know what time that happens at, right? And so those are happen at time n delta. So the question is, after a time t, how many of these steps have happened, and what is the probability that has decayed by then? And so, okay, you can write all of this in terms of, in very mathematical terms. But maybe we'll switch to the computer for now to see what actually happens. So I'm going to share my screen. If I can find the place to do that. Okay, now I'm going to find my notebook. Okay, so can you see my notebook?
Sure.
Okay.
You can make it a little bit bigger, maybe.
Yeah. So this is the function that we did last time to plot this cumulative distribution of, so we didn't do a function last time. I just took exactly the same code that we did last time, right, to plot these staircases. And I just put it in a function because we're going to use it a lot of times, right? So this is the first message that I want to drive home in terms of, having looked at some problem sets, etc. That anything that we repeat more than 2 times, more than twice, anything that we repeat more than twice, we have to automate. Right? So if we're going to plot a lot of cumulative functions,
not once.
Sorry?
Not once.
Not once.
I
don't know, if you're doing it twice, if you're doing it twice, sorry?
Some of my computer science colleagues would say that if you've done something manually twice, that's one too many times.
I think if you're doing it twice, then it's as much work to, you know, you can just copy and paste it. That's the same work as copying and pasting it and putting it in a function. But as soon as you use it 3 times, you're already doing too much work when you copy and paste it. But of course, the point is that usually you won't just repeat it exactly twice. You'll usually repeat it twice and then realize, oh no, there was something wrong, and you have to go back and change it. And then you do it in 2 places. And now you're doing it more than twice, and that's when you need to automate it. So yes, they're probably right that once you analyze it in the end, you need to probably do it, you know, as soon as you realize you're repeating something that you've already done, you just immediately put it in a function.
I actually think this really defines a computer scientist versus everybody else in terms of habits. Everybody else, it's like, oh, I don't want to think. Oh, I'll just copy and paste. Right.
That's probably true. Yeah.
Right. And computer scientists are, no, I don't want to ever repeat anything. I'm going to automate. I really think that makes a person a computer scientist.
Yeah. So actually, you know, yeah, the way I did this was literally take the notebook from last time, and there were all these cells that had pieces of this code, right? And it's actually pretty annoying to go through and copy from each cell, you know. So there is a way in Jupyter in the notebook of merging cells. So I could have done that. That's probably would have been a good idea. But it's actually pretty annoying to go through and pick them all out. So you could actually say, well, actually, I should have just been doing a function from the very start before I did any work. So basically, almost any calculation you should do, you should just immediately start writing a function for it, because you're bound to use it again, or you know, want to sort of somehow have it sort of in one block. Okay. Anyway, so this is exactly the code. I just put it all together, and I just you know, we'd fixed some values like 20, and I just changed them to variables. Okay. So what does this look like? So I need to load my plots package. And so now we know that this is called the cumulative distribution. So we're plotting the cumulative distribution of a geometric random variable, right? So this is the cumulative distribution of some geometric random variables. Oh yeah, so because the other thing I did was changed it so that I could have different deltas. Right, so last time we did this staircase, and we just had allowed it to be doing a staircase at times 1, you know, but now we want to allow it to do a staircase at time delta as well.
And there was an interpretation of this, right? The probability of recovering at time n, was it?
Yeah, yeah.
Can we put that in the comments somewhere?
I mean, that's what I've just been talking about, yeah.
Well, yes, but I don't see it visually.
Yeah, exactly.
I know you've been talking about it.
This is the probability that we have recovered by time n.
By time n, right? Yeah.
By, you know, at or before time n.
Good.
Yeah, so we need to put in the probability that, so the first argument is the probability that, you know, so I don't know, I think I've mentioned doc strings. So a doc string is a, you know, documentation string. So it's a string that describes the function. So I'm gonna just say sort of, and if I put backticks, it will put it in some, you know, so this is actually a markdown string. So if I put back p is the probability to decay at each time step. M is the total, you know, the total number of time steps. Delta, so I can actually make this a list as well with minus signs, and backslash delta tab is the time between steps. So I put that in at these triple quotes. That's just like in some other languages, that's a multiple line string. There's a single string, and I put it in before the function definition. So if I do that, then it will recognize that that is a string that is documenting this function, right? So I can actually put sort of, it's common to put this function signature as the first line. I indent it with a tab that will make it look like Julia code. And so when I do question mark plot cumulative, and I use the tab key there, plot cumulative, it will actually print out this doc string in a rather nice, cute way, right? And you can even put in LaTeX in there, right? So it turns out that this is like the probability density function, mass function, sorry, is f sub x of n equals p times 1 minus p to the power of n minus 1. That's LaTeX. I put it in $signs, and it didn't work. I don't put it in $signs. I put it in double backticks. I think, is that right? Yes. I put it in double backticks. There is some way of putting it in $signs, but I never remember how to do it. I put it in double backticks. That means math. That this is math. This backtick is this weird thing that's like the opposite of an apostrophe. It's going backwards, and it's somewhere in your keyboard, maybe hidden under some other key. You just have to find out how to write it on your particular keyboard. On my keyboard, it's, well, my keyboard is weird, so. Okay, so you put double backticks for maths, and then you get this beautiful doc string with, even a typeset LaTeX string in there. Okay. And I actually prefer not to put, if these are not really sentences, I don't put full stops, full points at the end. And then, whatever. There's, different people have different opinions about punctuation. Okay, so that's what plot cumulative does. Thanks for the suggestion to add that. So once I've added that, I don't really necessarily need this actual string, this actual comment here. Anyway, whatever. Okay, so plot cumulative, let's just put in some values. So last time we did 0.1, 20, and 1, right? So I actually put in a default value of delta equal to 1. So I can just leave that 1 out. And that should be exactly the same plot as we got last time. So I just literally took the code from last time, as I said, and so, I changed some things. I had to put in some deltas. So, the x's last time were just 1, 2, 3, 4, 5. Now they're 1 times delta. And remember that we had this weird thing where we had to offset the x and y by 1 to get this staircase. And then we get this function coming out. And what do we know about this function? So this is, you drew in problem set 2 the actual probability mass function, the probability that at time step n it decays, and that was an exponential that was falling off, some kind of exponential decay, right? And now we've summed that up from 0 up to n, so now we get something that's a sum of something that's sort of exponential. And what do we know about that? We know that the sum, of an infinite number of these things should give me 1. So we're seeing that this kind of curvy thing, this staircase, is asymptoting to 1, if that's a verb. Is asymptotic to 1, right? So I should add some labels. So x label n, and again, there is some way of making these into LaTeX, and I think we mentioned that the other day. Y label is cumulative probability, right? That's less than or equal to n. I'm not going to write it all out, but that's the idea. Okay. Great. So now what do we want to do? Now we want our other process where we take steps, for example, at times a half, right? So let's do that. So now we have this nice function. It's really easy to do that, right? That's the point of having a function. Now I just want to play around. I want to try out lots of things. So, I could be copying and pasting this all the time, but then I would have to go and figure out, oh yeah, there's n times delta. Now I need to replace that with a 0.1. Oh, and the deltas come somewhere else. Oh no, it doesn't. Oh yes, it does. It comes here, right? You don't want to go through that process. It's ridiculous. So you want to make a function that just summarizes everything you need, and then you forget about what's inside the function, and it becomes a sort of black box that you can now just use. But just like, so I actually used the function, no, I didn't. Yeah, I did. I used the function cumsum, which I asked you to write by hand in problem set 2. But once you've written it by hand once, then you realize, oh, Julia has this function. Then once you know what it's doing, you can just call the function and it becomes a black box, and it's just sort of another tool in your toolkit. You don't really want to ever write that again. Okay, so what do we want to do? We want to let's keep the same value of p, right? So I'm going to actually make p explicit over here. You don't want these magic numbers lying around, right? Just give them names. So delta, magic numbers just means numbers that appear in this call, and I just immediately forget what these numbers even mean, right? So let's just give them some names. Delta is now going to be 0.5. So what we're going to do is just start off with this same plot with this value of p and this value of n and just 1. Okay, that's a special magic number, right? 1 is a special. And now we're going to do the same thing with delta. So we're going to have an empty plot. Remember that that's just plot with empty parentheses. And then I'm going to add, so right, I wrote this function in such a way that everything gets added to the current plot, right? We have all of the plotting routines here. These two have bangs. So it's just going to add whatever it's plotting onto the current plot. Okay, so when we do that, it doesn't work. Dear. Why? Okay, so I just have to look, I know this is messy, but you just look right down and try and find out. So top level scope means like this code that I'm calling it in this sort of global scope outside any function. So it's telling me that that's at in 16 lines, and this colon 6 means at line 6. So if I actually put line numbers in, which I do by escape L, then it tells me that the problem is at this line, and then I go 1 up from that. So 1 up from this 5 is this 4, and it says the problem is in plot cumulative, and it's at in 11 at line 11. So let's go back to in 11 and put line numbers in with escape L. So which one you press escape and then separately press L, or alternatively control M and then press L. And so line 11. So here's the problem. Apparently, I don't know why that would be a problem. So probably I got N wrong.
I think P is a plot.
P is a plot. Classic mistake. Yeah, thank you. So I'm using P here, I wanted P to be 0.1 and pass in 0.1 here, but then I renamed P to be this plot object. And so, so this is where in a language like C, you would actually have to declare what types everything was, and it would give you an error immediately if you made them the same type. But in Julia, you can just rename, you can just redefine P to be some other type, and in this case, it's some really complicated type, that represents a plot object. So what am I going to do?
I see a major dilemma here because P is always probability and P is always plot. I don't see how you can fix this.
Right, so I'm just going to call that one PP, right? So I don't actually want, this P here is just because, in Julia, you might want to refer back to the plot, right? Especially if you're doing a for loop, which we might want to do at some point.
How about PL rather than PP?
PL, good. Okay, great. Thanks, Stan, for the observation. Okay, so when we get this pretty nice picture, right? So what's going on? So indeed, we see that this blue curve, so we should probably put some labels on, but maybe we can avoid it. So this one, label equals sort of delta equals 1, right? This one, label equals, by the way, how can I make this label delta equals, what should I put in here? Question for the chat. What should I put in here so that I get the value of delta in my label, the current value of delta? I don't know if we've actually discussed that. Have we? Does anybody remember?
String interpolation? I don't know if you've ever done that.
Okay, so we actually do
Somebody in the chat said put in the magic number.
No, we certainly do not put in the magic number. That is an immediate fail for the course.
That's the right answer.
Huh?
The 0.5 is the right answer.
I mean, I could put 0.5 here. Yeah, that's fine until I change this, right? Oh, what happened? Oh, I'm not allowed to. I didn't. Oh, damn. I didn't put
it. The label, yeah.
I have to put up the label in here. Oh, that's annoying. Yeah, I would have to. Okay, actually, maybe we should see how to do that. So you can have keyword arguments in Julia, and so you do semicolon separates normal arguments, which are called positional arguments, from keyword arguments. So I'm going to put label equals, and I'm going to give it a default value of nothing. And then I'm going to add to this plot command, label equals label. Okay, so it's a bit weird. So what's going on? So this means that I'm saying that this argument, this function plot cumulative can take one keyword argument, which is called label. And a keyword argument is different because you actually have to write the word label when you call the function if you want to use this keyword argument. This equals empty string is a default argument. So this will, by default, take the value empty string. And so I'll give a label, which is an empty string down here. So this label equals label is weird, but what's happening is that this right-hand label refers to this variable called label. And the left-hand label refers to the keyword argument of the plot function. So I happen to know that plot allows me to take, you happen to know it too, allows you to take a keyword, to give a keyword argument. So you have to specify the word label equals inside the plot command. And then this is going to be the value that I send into it. And that's going to be this keyword argument of this function that's called label. Okay, so this is a pretty common thing to do in Julia actually. Okay, so I'm going to re-evaluate that function with this extra label keyword, and then I'm going to run this function, and I should see what happened. No, that didn't work. Oh, because I turned off the legend at some point, probably. Yes, here, I turned off the legend. Leg equals false turns off the legend, so I don't want to do that anymore. So let me remove that. And then now I get a legend. Yes, great. And so
what would happen if I'm back to that line 5 if you just deleted PL equals?
Hold on. I don't want a label for the scatter plot that's separate, right? If line 5.
Line 5 on the very at the bottom. Go down.
Yep.
No. Not there.
Line
the very last, there you go, in of 22.
What would happen if I
deleted PL equals, if you just wrote plot parens? Why did you need that PL to clash with the P? Why do you need the PL equals?
I could just remove it, you mean? Yeah, okay, sure, I could. Yeah, but then I will now no longer able, so so later on we might want to do a for loop, and then I will need it. Oh, well, that's one way of doing it. Anyway, yeah, you're right. Let's just delete it. Okay, so that didn't work. Why didn't that work? Yeah, so no, let's see. I do need an empty plot though.
Yeah, I only said delete the P equals.
Right. Sorry. Yeah, I need an empty plot, which you can do with just plot bang. That just like clears the right. So without the bang, sorry, that makes a new plot. It's a bit confusing. Anyway, okay. So there we go. So delta equals 1 is this blue line with the red dots, and maybe I should have put the labels on the dots instead. Anyway, whatever. And the green line is delta equals 0.5. And the problem is now delta is already 0.4. I already changed that, and the label still says 0.5. So this is why you should never use magic numbers, because it's already wrong. That's just it, right? So anybody who uses magic numbers immediately fails the course. I mean, not actually, but morally. Morally, you'll fail the course if you use magic numbers in your code.
You're going to give the students a heart attack.
Good.
Tell them that.
That way they won't use magic numbers, and we'll have achieved the goal. So what I need here is the value of delta, right? I need the current value of delta equals delta, the symbol delta, right? I need the current value of delta, so it should just be that. What's going to happen when I run the code? Well, let's do it. Well, hopefully you're saying to yourself what's going to happen, and hopefully you're saying to yourself, oh, this is a string, and so it's just going to copy that string, right? So this question mark here is because in order to use, this is a Unicode character. In order to use a Unicode character, I actually need to set up something for some reason. I need to do some command to make the plotting program GR, which is what we're using, use Unicode. There's some magic incantation that you have to do that I never remember, so we won't do it. But anyway, the point is that it's trying to print the string delta there, right? This is a string, and it's trying to just print that string here. But I don't want that string. I want the value of delta, the numerical value. So I actually want to insert this numerical value into the string. That's called string interpolation, as Alan said, and I do that with this $sign. So $ delta means the value of the string, right? So $A inserts the value of the variable A into the string. When I do that, I indeed get the current value of delta right there. Great. And by the way, often you'll actually need parentheses. So you don't need parentheses if it's just the value, but if you want like 1 minus delta or something, you can actually put arbitrary Julia, or I don't know, arbitrary, pretty complicated Julia code here, and it will evaluate this value and put that instead of this whole parenthesis. Okay, but we just want the value of delta, so we'll just put, let's put the parentheses just for good measure. It's probably clearer. Okay, great. So what have we just established? We've established, looking at this graph, that we have nothing like, right? If what we're trying to do is find, what is this P of delta? Yeah, so I should probably write P of delta here and yeah, whatever. So if we use the same P, but we have delta that is half as big, what happens is, of course, the same number of people are decaying, right? You can see that the heights of these things are the same, but of course they're decaying much faster. And so the curve is nowhere near my original curve, obviously. It's decaying far too fast. And so what I need to do is change this value of P that I'm using in my second plot so that it sort of lines up, right? And so I could do, my usual, what I usually like to do in these situations, using interact, and then we're actually gonna put an interactive plot in here. So at manipulate, we're gonna vary the P, the new P, right? So let's call new P. So I'm gonna have the old P still be 0.1. And I'll manipulate new P from, how does it, I've forgotten how to do a manipulate. For new P in, let's call it P2 in 0.1 with steps of 0.1 up to 1.0, say. So I'll indent all of these things. All of those are going inside the manipulate. It makes a new plot each time, very important. If I don't put that in, then it'll just, keep adding more and more curves and it'll become a horrible mess. I need a new plot each time. So I could do that by making, a plot cumulative without a bang that creates a new plot, but it's easier just to clean the plot with this plot command. And now I need a P2 in here, right? And so I'm keeping the same delta, but I'm manipulating P2. And when I do that, and the same P, right? So the original process is the same. And so this is compiling interact. And the new process has this different P2 that I'm going to be able to change. So this is what it looks like. So when P2 is very high, of course, it decays very fast. It goes very quickly to everybody recovered. And as I change this, I should see this moving if my interact is working. So sorry for those who still haven't got interact working. I don't know what's going on there. Let's add a few more values of n. Actually, we should probably fix the n for the top one. We should fix that to 20, right? No, 40 or something. Okay. And I should probably fix the x and y limits I should also fix, right? So that was another comment on your problem sets. Almost always you want to fix the x and y limits of your plots if you're manipulating them, because otherwise you'll get plots that keep changing size every time you move your sliders, which is really annoying. So x limits is going from 0 to 40, and y limits is going from 0 to 1. We should always put spaces after commas. Okay, so now it's all much more satisfactory, and we see that, okay, yeah, as I move my slider, there's some magic value, which I can't quite, maybe it's there, where they fall on top of each other. So for that particular value of P2, which is 0.04, happens to be 0.04 in this particular case. Why is it 0.04? Okay, yeah, it happens to be 0.04. Right, 0.05, which you might have guessed, actually doesn't. Yeah, okay, it's because delta is 0.4 instead of 0.8. I was thinking of having delta as 0.5. being exactly half as often. Let's do that. Delta is 0.5, as exactly half as often. So when do they line up? They line up when delta is when P2 is 0.05. So P2 is half of P1, which is what you might have guessed, right? But you can just, it's nice that you can, in this particular case, it's sort of nice because it's reasonable that they're about, you just have to sort of divide it by 2. But in some more general case, that might not be the case. And then you can just use this interact to sort of guess what's going on these, right? I think it's pretty cool. Okay. So how are we doing on time? Okay. So, so we found that, we need to decrease P2, and indeed, we need to take it approximately half as big if the delta is half as big, right? Okay, so how can we work out exactly what's going on here? So, well, we have so in the problem set 2, you found that the cumulative distribution function, which we haven't quite named that, but the cumulative distribution function for a geometric random variable, geom of n comma p, geom of p. So, probability people like to write it as x twiddles geom of p. So text geom of p, I guess. Okay, so x is a random variable with distribution, geometric distribution with parameter p. We have that you found, hopefully, if you did the analytic calculation that it asked for, which a lot of people didn't for some reason, or if they didn't write it out, they just gave the answer, which is, you're supposed to write it out if it asks you to give it, right? So that was, you should have found that it's 1 minus p to the power n. Right, so that is the probability that you have decayed by time n, up to or including time n. You should have come out to this nice simple expression, 1 minus p to the n, right? Because there's a p in there, but that cancels with the denominator, which is 1 minus brackets 1 minus p. Okay, so that's good. And then we have f of y. Y is my other geometric random variable, which is decaying at other times. And that is 1 minus p2 to the power n, right? Right? But, okay, this is where the notation gets a bit annoying. So that is, the number, that is the, what is that? That's the probability that you have decayed by time step number n. But we actually want the probability that you decay by time n, by time t. So yeah, the notation gets annoying because we have to start using all these floors everywhere and whatever. So let's just forget about the notation. I wrote it out in some detail in the notes, in the slides. But so basically, I'm just going to say, when are these, at what time, well, let's fix a time n. Fix a time t equals n. I want to find the value of P2, the value of this decay. Well, okay, this is actually what I call P of delta, right? So this is like f of y sub delta. F of y sub delta, and this is P of delta. So I've got this thing all to the power n. So I've got something like that, right? Yeah, so that's after n time steps. But I want to fix an actual real time t. I want to find the P of delta such that sort of f, such that the probabilities are the same at that time. Probabilities are the same at time t. Okay, so how do I do that? So I'm going to have 1 minus p of delta to the power of n. But n, so okay, so what is time t? time t is actually n times delta, right? So n is actually t over delta. Okay, so this up here, I get t over delta. And so that is supposed to be equal to 1 minus p to the power n. So actually I have this equality, no, and this is t in here. I actually have this equality that I have to solve. And I want to solve that for p of delta. Everything else I know. And so exercise, solve for p of delta. You can actually find exactly the right value of delta that will give you exactly the same values at each integer time t, right? So we saw that it's going to be something like p of delta is approximately some like proportional to delta, basically. So that's one way of doing it, and but actually we're really interested in the continuous limit. Right? What does that mean? It means we're interested in the limit when delta goes to 0. So I want to take finer and finer steps, shorter and shorter steps, and take the limit when actually I sort of take one step I take steps all the time, right? In some sense. So how can I do that? Any suggestions on the chat? So I want to analyze this distribution function that I highlighted as delta goes to 0. So what could I do? How could I get that limit? I'm going to approximate something in that expression. When delta goes to 0, what can I approximate? Well, I guess I should say something else. So when delta goes to 0, it's sort of clear from this stuff here. If I keep taking delta and delta smaller and smaller, but I keep the same value of p, for example, then I'll just get something steeper and steeper, and it'll immediately just all recover immediately. And so that's obviously not what I want. And so I definitely need, I need that this p of delta goes to 0 as well. So the probability of decaying at each time step has to get smaller when delta gets smaller. And it has to get smaller in a certain way. That's what we want to find. And so now, with that extra information, what can we approximate here? Anybody have any suggestions in the chat? I just always lose track of all these windows. There we go. No. Okay. Okay, no suggestions. Okay, so we're going to use a trick, of course.
So is the trick going to come from combinatorics, probability?
The trick's going to come. So there are different ways of doing it. So basically, it's going to come from calculus.
Well, that was going to be the fourth multiple choice.
Yeah. This trick's going to come from calculus. Anybody have a calculus idea here that we could use?
So let's understand let's remind ourselves what the question is here.
Yeah.
So in summary, we've got a fixed p, and you want
what?
Well,
yeah.
You do.
Yeah. Okay. So I guess my notation might be a bit confusing. So this is the original p.
Right.
This is the probability of decaying each day. And then
and now you want to find you want to find the p of delta,
which is a function of delta, right? As I change delta, which is the new time steps in my new process, where I'm measuring the decay now. I measure the decay after each time step of length delta.
Right, and because they're smaller time steps, you expect the probability of recovery to be a lot smaller because they're going to somehow add up in some crazy way. But
exactly.
But if you take a very, very tiny step, nothing much is going to change. You're not going to recover that fast.
Exactly. Yeah. So rather than adding up, they're going to multiply up. Yeah, basically. So can anybody find a way of approximating some part of this expression for small when p of delta is very small?
So I would think a little. Yeah. All right. I'm not going to say anything. There's some text coming up.
Derivative. Isn't that left-hand limit going to be 1 minus e, something like that? Yeah. Okay. So we're going to use a result from calculus that says 1 minus x. So if x is very small, how can I approximate? So I have this 1 minus something, and that something is going to 0. So it's going to be very small, right? If I take a small enough delta. How can I approximate 1 minus x? Well, I can approximate it with some particular function that you all know and love, hopefully.
1.
What might that
If
function?
x is really small, I could approximate it by 1.
Okay, I could approximate it by 1, but then I just get 1 minus, this 1 minus something gives me 0, and so I just get 1 here. And so that's not very useful.
Well, I mean, maybe x isn't quite that small.
Right.
Small, but it's not that small.
Okay, right. So I need something that depends on x, yeah. So 1 minus x, do you know any functions that behave like 1 minus x when x is very small?
Lots of functions.
Yeah, one in particular that we like.
1 minus sine x.
True.
That's not the one you're looking for?
That's not the right one. No.
Somehow I didn't think so.
No. It's a very famous function that I'm looking for. Okay, nobody. So I'm not going to wait around forever. So this is going to be the exponential. Oh, the exponential of minus x. Okay, so that's a very important thing to remember, that the exponential of minus x for small x can be expanded as a series in x, right? So let's just remember that. So x of positive x is going to be 1 plus x plus a half x squared plus 1 over 3 factorial, which is 6 times x cubed plus etc. So that's an infinite series in powers of x. This is like so where does that come from? That comes from the fact that we define the exponential function as the function which is equal to its own derivative. Right, so if I have a function f and I say f, I'm defining my function to be the function which is equal to its own derivative, then if you assume that you can write it as a power series, this expansion with x to the n with some coefficient an, if you do the calculation, you'll find that those coefficients have to be given by 1 over n factorial. So I should actually write the general term. 1 over n factorial times x to the n, and that goes on forever. So I can write that as a sum, an infinite sum of n equals 0 up to infinity of this thing, right? Okay, so that comes from, yeah, as I said, as a function was equal to its derivative, and suppose that I can write it as a power series. X.
So how good is that? If I go x with 1.01.
Yeah, good idea. So
Sure.
so that's x with x, where x is positive. If x is negative, then I do 1 minus x plus a half x squared minus a third x cubed, etc.
All right, so let's go x with minus 0.01.
X, sorry?
Let's go x of minus 0.01.
Well, let's do x equals 0.1, and let's do 1 minus x is 0.99, and now let's do x of minus x. And that gives me something that's close to 0.99. So they're not exactly the same. They differ. How much do they differ by? They differ by something like x squared, right? How big is x? Not x squared. Yeah.
X squared over 2.
Yeah, x squared. Yeah. How big is x squared? It's 10 to the minus 4.
X squared over 2 is even better.
X squared over 2. Yeah. So they differ by about 5 times 10 to the minus 5. And if you look, the difference is indeed about 1, 2, 3, 4, 5 times 10 to the minus 5. Yeah. Thanks. Okay. Great. So that was a good idea. So now I just put that in my expression. I know the maths is a bit heavy, but sorry about that. But so I replace 1 minus p delta, p of delta. And so that's going to be approximately equal to 1 minus exponential of minus P of delta. And then I take all of that to the power T over delta. And I get that. And now what do? I have an exponential of something to the power of something. Now what do I do with that? So that's a power T to the delta, T over delta. Right, that's what I have. So 1 minus exponential of that. I should have done this on the iPad probably. I have to remember my rules of exponentials. I have exponential of some number A to the power of some number B. What do I get? I get exponential of A times B. And so this is exponential of minus P to the delta times T over delta. And so what do we see? As delta goes to 0, what I want to do is I need P of delta over delta. The only way that I'm going to get something reasonable out of this thing when I take this limit is if P of delta over delta converges to some finite number. Converges when delta goes to 0, converges to some number lambda. Okay, and so the end result is some f of t, which is 1 minus exponential of minus lambda times t. And so we call lambda the rate. It's called a rate. And what is that? It's a probability per unit time decaying. So approximately in a small time, delta t, I'll decay with probability lambda times delta t.
And lambda is that original P, like whatever that was, 0.5 or something that you had, right? Isn't lambda correspond to?
Oh yeah, so if I want, okay, so that was in general, yeah, so thanks. So if I want to reproduce the original thing, then I need to take a particular value of lambda, and so you would have to work out what that value of lambda is, but maybe, is it exactly equal to P?
Well, what was the formula on the right-hand side? Wasn't it?
No, I don't think it's exactly equal to P in general.
Oh,
right, on the right-hand side it had 1 minus P to the power T. And so I want to put x of minus lambda t equal to 1 minus P.
oh,
Yeah, so I have to choose lambda such that, yeah, right. So I have to choose lambda such that 1 minus P is equal to x of lambda, basically, x of minus lambda or something.
yes, there's a logarithm involved.
Okay, so, it's a bit hairy. But anyway, the point is we've arrived at something very important, which is what? We've actually got a function as a continuous function of t, right? So let's plot that. So plot cumulative, my original p, which is 0.1, so I'm going to just immediately ignore all the rules I put about not using magic numbers. So plot, there's my original thing, and now I'm going to add to that the function x goes to 1 minus x of minus lambda t. I should do a manipulate. I'm running out of time, so maybe we can do that next time. Sorry, lambda t times t. And t goes to that. Oh, come on. Lambda equals 0.1. So let's try the same value, 0.1. And we see that, okay, it is fitting, I don't understand why that doesn't. Okay, let's make it a bit thicker. So you see that, it's definitely close. I'm not convinced it's exactly correct, but I think it's just correct because this value is so high, right? So let's call So low. So if we put p equals 0.5 instead and lambda equals 0.5, then I think it won't work. Yeah. So it's not quite right. It was only because when p is small, it's approximately equal to p. But
Yeah, you need the log, right?
Yeah, you need
That's what we
log.
said.
Right. So what is it? Log of
minus log of 1 minus p. Minus log.
minus log of 1 minus p. Yeah.
There you go.
Okay, so if we use minus log of 1 minus p in this continuous thing, then we exactly reproduce the original, right? But the point is that we really have reached a thing which we can regard as a process in continuous time with a certain probability sort of at each moment to decay. And so this is cool. So this is, you know, the thing which is doing the value which you have at time t is called an exponential random variable. And so what we've calculated is what? Well, it's the probability. So let's call it z. The probability that z is less than or equal to t for any continuous value t. That's what we've calculated. So we'll call that f sub z of t. That's the cumulative distribution function for any real t of this random variable, which is a continuous valued random variable. It can take any value t.
So David, if I want to understand, I mean, there was a lot of confusing notation and all, but if you could just let me see your graph, just to scroll down a tiny bit, so I could just see the full bit of your plot, if you don't mind. What I think you did in the end was, I mean, it seemed a little complicated, but really it was just an interpolation problem. You had those red dots at equally spaced points, and you wanted a nice smooth curve through them, right? I mean, that's kind of really all you wanted.
Okay, sure.
And you spent, you know, maybe the last 15 minutes, I didn't really keep track, finding what would do that. Would that be a summary of?
That's sort of what I did.
And yeah.
I did something more than that, right? There's not, yeah, okay. But I'm actually thinking of this process where I decay, you know, at finer and finer, allow myself to decay at finer and finer times. I actually there's a kind of complicated limit. So basically what I'm doing is say, you know, I have all these staircase functions at with different widths, and I'm taking the limit as I take the width of the staircase.
Could I have gone the other way? Could I have like drawn a smooth curve and then like looked at it at finer and finer equally spaced points and asked what was happening?
Sure. Yes. Good idea. Yes. But I don't know. I mean, because this isn't, you know, this is an example of this process called taking the continuous limit, which is, you know, something that in more advanced probability courses you do in more advanced settings. So like, you know, if you have a random walk process, then you want to take the limit as the jumps of the random walk get closer and closer together, but also smaller and smaller. And that is a pretty complicated, actually, object to deal with.
But in the end, no matter when you do that, you always want it to be just a, I mean, like people make a big deal about the continuous and the discrete. Like the continuous is much harder, the discrete's much easier to understand. But I mean, if you just think of it as you just want a smoothed out version of what you're already doing.
Right.
It doesn't seem so scary to me. I don't know. It doesn't seem
yeah. No, you're right. You're right.
To me.
Yeah.
So
okay, I guess we should stop there, unfortunately.
Sorry?
I said I guess we should stop there.
Oh yeah, we're out of time. That is true.
Yeah.
Okay.
Yeah, but you're right. You're right. Definitely. That's a nice way of thinking about it.
All right. So see everybody on Wednesday.
Everybody. See you on Wednesday. No. Yeah, Wednesday. Yeah.
Yep. Today's Monday. Yep.
Okay. Okay. Bye.